Yes, you'll be able to see now.
Yes, sir.
Yeah. Okay, let me start. As I said, we will be discussing today about Module 4. Okay, the title of the Module 4 is this digital transmission through band limited additive white Gaussian noise channels. Okay, so here catchy words are band limited. Okay, means we are discussing about how to transmit the signals, okay, over a band limited additive white Gaussian noise channels. Okay, that too the digital transmission means what should be the shape of the input signal. Okay, what is the optimum or better shape, so which will avoid the disturbances or side effects which causes on the signal. Okay, so in this module, basically, we will be discussing about the design of band limited signals. Okay, the design of the band limited signals. So before that, let me ask you. Already I'm showing the slide. So the moment I say the band limited channel, okay, so in practice, okay, there are so many channels are of band limited in nature, like telephone channel, okay, then microwave, line of sight radio channels, satellite channels, even underwater acoustic channels. They're all band limited. So, what do you mean by band limited? Band limited. What do you understand by band limited?
Only a particular frequency range is allowed to pass through.
Yeah, means that channel allows only certain range of frequencies. That's all, isn't it? So, if the input signal, okay, band is more than the bandwidth of the channel, then it may not pass that part of the signal, right? Isn't it? So that is what the meaning of band limited. So it can pass only a certain range of frequencies. So as I said, telephone channel. Any idea what is the bandwidth of telephone channel? Wired one earlier, telephone, no landline connections. For that, what is the bandwidth we say? I think this I repeated many times. Telephone channels. I used to say what is the voice frequency range, at what rate it will be sampled and then quantized and it will be transmitted over the line, and what type of modulation also we use for that. Yes, come on, pass quickly, should respond.
About 3000 hertz, sir.
Yeah, 3400 hertz to 4000 hertz. That we say the voice frequency is from 300 hertz to 3400 hertz. So it will be rounded off to 4000 hertz. Means we say 4 kilohertz is the maximum voice frequency range. And it will be sampled at what rate? Twice the highest frequency of that signal. Means it will be sampled at 8 kilohertz. And we do the quantization at then we represent each sampled and quantized data with 8 bits, right? So with that we get 64 kbps. Okay, 64,000 kilobits per second is the this one telephone channel bandwidth, right? uh, Fine. So as I said, we will be discussing about the signal design, right? What should be the shape of the signal to transmit over a limited bandwidth channel. And to do that, we are first modeling the channel as a linear filter. Okay. The moment I say filter, I hope you will be able to visualize what type of filters you have studied so far. Is it possible to say from your side? What are the different types of filters you have studied so far in your
Low
curriculum?
pass filter, high pass filter, band pass filter,
Yeah,
band
very
stop
good.
filter.
Yeah. See, low pass filter, high pass filter, band pass filter, band reject filter, and so on. You have studied, right? So, if I say low pass filter, then what it does means it passes only the low frequency signal, right? Yes or no?
Yes, sir.
Yeah, if it is high pass filter, it passes frequencies after a certain cutoff frequency, right? So below that it will not pass. So band pass filter means it passes only certain range of frequencies, say from F1 to F2 hertz, like that. So band reject means it rejects certain range of frequencies, like that. Fine. So here, as I said about the discussion of band limited channel, and I said it will be modeled as a linear filter, right? So when we are modeling as a linear filter with the bandwidth limitation, right? So this bandwidth limitation uh, imposes the constraint on the bandwidth of the transmitted signal, right? That's what I'm saying here. The transmitted signals must be designed to satisfy the bandwidth constraint imposed by the channel. So that is, the transmitted signals must be shaped to restrict their bandwidth, okay, to that of the available channel. I think we have discussed about a variety of line codes, right? Unipolar, polar, that is NRZ and RZ, return to zero, non-return to zero, right? Then bipolar coding, Manchester coding, right? So I discussed during that time what is the power spectral density of each of the line code and what is the amount of bandwidth required for transmitting each of those line codes. Okay, means if I transmit digital information, zeros and ones, by using certain line code, so I will be able to say, yes, this much bandwidth is required for this particular line code. Isn't it? Have you studied about that? I remembered what I have discussed before COVID-19, this one, lockdown.
Yes, sir.
Different types of line codes, which is module one's content. Okay, unipolar, polar, bipolar, then Manchester line coding, right? So just if go back and anyway you have to study for test, so just have a look, then you will understand. Oh, this is what the limitation of each line code. Okay, so since the channel bandwidth is limited, right? So this linear filter, okay, I am modeling that, means I am modeling channel as a linear filter with a bandwidth limitation. So that distorts the signal. Okay, when the signal is transmitted through the channel, it is getting distorted. Okay, so that distortion, means channel distortion, results in inter-symbol interference. Okay, fine. So that leads to, means that results in inter-symbol interference into the output of the demodulator. That symbol interference causes to increase the probability of error in the detector. This inter-symbol interference, name only says inter-symbol interference. See, symbol is nothing but what zeros and ones, right? So inter means one symbol duration will be overlapping with the another symbol duration, right? So due to that, there will be an interference. So that we call as an inter-symbol interference. So why inter-symbol interference happens? This results due to distortions in the channel. Means as the signal transmitted over this channel, so the signal will be getting delayed, okay, by some amount of time with the consecutive bits. So that leads to overlap of the symbols with the adjacent bits. That we call it as an inter-symbol interference. So that leads to increase in the probability of error in the detector. Okay, so we will be discussing how to minimize or how do we correct this error. Means we will be discussing about the devices or methods for correcting this channel distortion. So those devices or methods, we call it as a channel equalizers. Okay, so we will be discussing about that also in detail about what are the different types of channel equalizers, linear, then adaptive, and so on. Okay, so this is what the overview of this module 4. As I said, we will be concentrating on the design of the band limited signals. Okay, so here we discuss what is the Nyquist criteria to have zero inter-symbol interference. Okay, since I said the channel distortion leads to what ISI, right? that leads to probability of error in the detector. So how do we means to get zero inter-symbol interference? What is the Nyquist? So Nyquist has suggested some criteria. Okay, if the shape of the pulse is like this, then I can have a zero inter-symbol interference ideally. Then there are other versions of that is a partial response duobinary signaling and other things. We will be discussing about that in this model. Okay. So is it clear what we discuss in this model? I said about the different design of band limited signals. That is then Nyquist criteria to have zero inter-symbol interference. Then next question is a duobinary signaling. Okay. Then we'll be discussing about this inter-symbol interference. Means how do we minimize this and all. Then how do we correct this inter-symbol interference? What is the methods or devices? That is known as channel equalizers. Okay. Fine. So as I said, the band limited channels, right? So just I wanted to show with some pictures. So you're all aware what it is. What is this one? Anybody can guess what it is? Hello?
Antenna.
What it is? What is the diagram I'm showing?
Antenna.
Antenna, right? So it is a tower, basically. Wireless tower it is, right? And you are all very much aware of this Wi-Fi, right? And just to show it is 4G network. Okay. So I said Wi-Fi will be operated in the ISM band, right? Industry, scientific, and medical band, that is unlicensed version. And each channel will be having a bandwidth of 20 megahertz, right? And this 4G network. So what is the name of 4G network? Anyone can say? 4G, right now you are using this 4G. What is the name of the network?
LTE.
Yeah, LTE. That is long-term evolution, right? LTE. So this 4G can be operated in these different bands. Even 1.4 megahertz is also there. I have not shown that. 3 megahertz, 5 megahertz, 10 megahertz, 15 megahertz, and 20 megahertz. Okay. So these are the different bandwidths supported by that network. Because what I mean to say is these are all band limited channels, right? So 4G, these are the different bandwidths which are available to the service provider to accommodate the users. So this is about one thing. To say is a band limited channel. So next one is I said satellite channels, right? Just showing the picture with the satellite and next what I said about microwave line of sight channels, right? So just it is one network. So this is one antenna, means base station only, what I have shown in the first slide, and this is another antenna. So these two are connected, okay, through microwave. That is why it is here it is written C band, Q band, K band. So these are all this is for the backhaul link, right? I think you might be knowing what is the frequency range of C band, Q band, and K band. I have said in microwave. Said or not? What is the C band frequency range? You know, C band
So
frequency.
4 to 8 gigahertz.
Pardon?
4 to 8 gigahertz.
4 to 8 gigahertz. Good. So that is a C band frequency range, right? Like that X band. X band also you studied, no? And yeah, what is the frequency range of X band?
8 to 12, sir.
Yeah,
8
8
to 12
gigahertz
gigahertz.
to 8 gigahertz to 12 gigahertz, which you do or you're conducting experiments in the laboratory, right? So whatever the equipments we are having in our laboratory, microwave laboratory, they will be operated in the 8 gigahertz to 12 gigahertz. That is X band. Okay, just it is to show this is about the microwave line of sight link. It is okay. This is a network. Actually, it is a cellular network, EPC core network EPC, which is connected to the microcell base station, right? And these two towers are connected wirelessly. So, and they are in the line of sight. And another thing is this. I think this figure also you might have seen. So this is the terrestrial microwave communication, right? like one example. So they're all band limited, what I mean to say. Okay, there's a micro line of sight radio channels. And just to give another about acoustic channels, shown some pictures. Okay, so this is underwater acoustic channel. So here sound source, and here a boat is there. Right? So direct path, then reflection path, and all. So they're all band limited to say. Means it works at certain frequency. Okay, so to come to the actual content of your this one is this. That is the digital transmission through band limited channels. As I said, the channel will be modeled as a linear filter, right? Channel will be modeled as a linear filter with bandwidth limitation, right? So its impulse response, the impulse response of that filter is denoted by C of t. The C of t is the impulse response of the linear filter. And in frequency domain, we say it is C of f. Okay. So I hope you will be able to visualize if I say it is a linear filter, that is LTA system, right? So input is something and output will get something. So output will be what? Convolution of input and the impulse response of the LTA system, right? So the frequency response C of f of the linear filter will be this one. So integral from minus infinity to infinity C of t into e power minus j 2 pi f t into dt. So in frequency domain we write like this, right? So to say the channel is a baseband means it is a low frequency, right? Baseband channel. So that is band limited to certain frequency, that is BC hertz. Okay. And the frequency response of the channel, as I said, C of f will be equal to 0 when f is greater than this frequency, BC hertz. Okay. So I hope you'll be able to visualize this. So how do we write C of f? I said C of f is our frequency response of the impulse response of the linear filter. So I am writing it is integral from 0 to infinity, that is from minus to infinity, C of t e power minus j 2 pi f t into dt. I said this that if the channel is a baseband channel, that is band limited to certain frequency, that is BC hertz, right? Then the value of C of f will be 0 when f is greater than this BC hertz. Okay. So any frequency component with frequencies higher than this BC hertz will not be passed by the channel. Hence, we say it is band limited to certain frequencies. So that we denote it by W, which is equal to BC hertz. Okay. So I think this you would have visualized so far. So this is the magnitude response of the frequency response of that filter. Okay. So it frequency is from what? Minus BC hertz to BC hertz, right? That is what? This is the frequency response of the low pass filter, na? It is from 0 to BC hertz. Hope is it clear? This picture is clear?
Yes, sir.
See, if I consider only the positive frequencies from 0 to BC hertz, it is what? Frequency response of the low pass filter, isn't it? It passes only the low frequencies. Means this channel restricts the signal to be transmitted from 0 to BC hertz. So this is the magnitude response and this is the phase response of that filter. So shall I go to the next slide? If it is clear about this frequency response and the phase response of that filter. Okay, so as I was telling, the frequency response, right, of the linear filter will be written as the C of f is equal to this integral from minus infinity to infinity C of t into e power minus j 2 pi f t into dt. Right, and this is what I said about the magnitude and phase response of that filter. Okay, so let me denote the bandwidth limitation of the signal and as well as channel as W hertz. Okay, so let W hertz denotes the what? Bandwidth limitation of the signal and as well as the channel. Suppose if I consider the input to the band limited channel is a signal, which is denoted as GT of T. So I'm representing the input signal, which is also band limited to watt hertz, W hertz. Channel is also band limited to watt frequency, W hertz. Right? So that will be applied to the channel. Right? So the output of the channel corresponding to this input GT of T will be written as, so H of T will be equal to what I said. See, output of the filter, I am representing it as H of T. Right? GT of T is the input, and C of T is the impulse response of the filter. So H of T, as I said, it is the output of the channel. So which is equal to what? It will be convolution of input and the frequency response, or even impulse response of the filter. Right? So that is what is written. H of T is equal to C of T convolved with GT of T. I hope is it clear, this equation. As I said, C of T is the impulse response of the channel. I am making channel as a linear filter, and GT of T is the what? It is my input signal, which is to be transmitted over the channel, right? So convolution of these two will be the what? Output of that channel. Okay. So we know how to write this convolution integral, right? So C of T is the impulse response of the channel. So shifted version of the input signal, shifted and folded and shifted version, right, of that signal. So this is a convolution integral, right? So I can say H of T is convolution of impulse response of the filter and as well as the input transmitted input signal. In frequency domain, we all know convolution of two signals in time domain will be equal to what? Multiplication of their Fourier transform in the frequency domain. Hence, I am writing H of F will be equal to C of F into GT of F. Okay. So I hope there will be no issues with these equations, starting from writing equation of impulse response of a channel in frequency domain to this. Right? So GT of F is the what? Fourier transform of the transmitted signal GT of T. Right? And H of F is the spectrum of H of T. That is the output of the channel. Yes, any issues with these equations?
No, sir.
No issues, no? I think, I hope it is clear. Okay. So this is what I wanted to say. This diagram was from the beginning, I think. See, GT of T is the signal to be transmitted, right? Transmitted signal. And I am modeling channel as a linear filter with impulse response C of T. In frequency domain, it is C of F. So output of the channel is H of T, right? And here, I am assuming the additive weight Gaussian noise. N of T is the additive weight Gaussian noise that will be added to the output of the channel. So in channel, we say noise is added, right? So R of T is the received signal at the receiver side. So which is equal to what? H of T plus N of T. Okay. So R of T is equal to H of T plus N of T. Right? Okay. So as I said, the signal at the input to the demodulator, that is output of the channel, right, is corrupted by this additive weight Gaussian noise channel. So which is given by what I said, H of T plus N of T is the received signal. Okay. So, sorry, in the presence of additive weight Gaussian noise, okay, I think we have discussed about matched filter. Remembered? Hello, have you remembered about the matched filter?
Yes, sir. Yes, sir.
What about others? Only Pranav, Vishnu, and other people are responding. Other people? And Siri, Saujana responding. Chandan is responding. Other people are not responding. Okay. So let me say a few words about master filter again, because understanding of master filter plays an important role here. Okay, because if you know clearly about that master filter, then working of this will be clear, right? So anyone can say what the master filter is from your end? What you have studied so far or not? Or only heard my lecture and left? I think that is in module 2. Module 2 last topic was the master filter. Any idea? Yes? Any idea? No idea.
It is to
Yeah.
increase our
Yeah.
SNR ratio, sir.
Very good. So means if I sample at t equal to t, the signal to noise ratio will be maximum, isn't it? The SNR will be maximum. So I think I will come back to that. Okay, so what I am going to say is, so this is about the channel modeling, right? I am modeling this as a linear filter, then output of that is h of t, additive weight Gaussian noise will be added to that. So this is the received signal, right? R of t is h of t plus n of t. So we need to visualize now receiver. Okay, so I am saying let the received signal R of t, which is h of t plus n of t, is passed through the matched filter. So that has the frequency response of this. Okay, the received signal will be passed through the matched filter. So that matched filter has a frequency response of this. So I am denoting G R of f, G suffix R of f to indicate this is the receiver matched filter frequency response. So that is H conjugate of f into e power minus j 2 pi of t naught, where this t naught is the time delay at the filter output. Okay. T naught is the time delay at which the filter output is sampled. Fine. So the signal component at the output of the master filter at the sampling instant t equal to t naught is given by this formula. That is y s of t naught is equal to integral from minus to infinity h of square into df. So if I substitute that value, I will be getting the value as EH, where EH is the energy in the channel output, which is the energy in the channel output H of t. So the noise component at the output of the matched filter, okay, the noise component at the output of the matched filter, as we are aware, it has a zero mean and the power spectral density of that noise will be given as S n of f will be equal to n naught by 2 into h of f square. Okay, so this is the power spectral density of the noise signal, and the variance that is the noise power at the output of the master filter has variance. So for that, the formula is that sigma square n is equal to integral from minus into infinity S n of f into df. So if I substitute the value of S n of f as that, what is that? N naught by 2 into h of f square. So I will be getting that as n naught into h by 2. So this is the variance. Okay. I think you are aware of these things, mean, variance, right? It means the additive weight Gaussian noise has zero mean and variance has n naught into h by 2, right? So if I calculate what is the output SNR, right, that is signal to noise ratio, it is the output of the matched filter is written as S by N output, okay, which is equal to, this is a signal power. So signal is what I said, EH, right? So E squared H, and this is the noise power, that is n naught into H by 2. Right, so one EH will get cancelled. I will be able to write it as 2 EH by N naught. So this is the signal to noise ratio at the output of the matched filter. Okay. So the filter impulse response, okay, is matched to the signal component H of t in the received signal here, okay, instead of the transmitted signal. So in the earlier case, when we were discussed about master filter, there we used to match the impulse response of the master filter to the transmit signal. Here we need to match the impulse response of master filter should be matched to the transmit this one h of t. Okay. So what I wanted to say is to implement the matched filter at the receiver with an impulse response of h of t, right? So, or equivalent to what I can say, the impulse response of the C of t, C of t must be known to the receiver. Means the master filter should be aware of the impulse response of the channel. That's what the meaning is. Okay? If I want to implement the master filter at the receiver should be aware of what is the impulse response of the channel. So the performance of that system is determined the signal energy of the output of the channel, that is EH, right? So if I want to maximize the received signal to noise ratio, we should ensure that the spectrum of the transmitted signal waveform GT of t is limited to the bandwidth of the channel. So this is what I wanted to convey about that. So I hope I don't know to what extent you could grasp these equations. That is master filter. When I pass that received signal through a master filter, and that master filter has a frequency response of this I said, right? GR of f is equal to h conjugate of f d power minus j2 by f t naught. Then I will be sampling that at a t equal to t dot. Then output of the master filter will be this, right? And I'm talking about what is the power spectral density of the noise component which is there at the output of the master filter, and what is its variance. Okay, and then I found what is the output SNR, right? So to maximize output SNR, what is the condition? Means I said that we have to restrict the spectrum of the transmitted signal to a bandwidth of the channel. Then it is possible to maximize the received signal to noise ratio to the output of the receiver. So, and this is what one example. So I'm not going with that mathematical equations. You can refer the textbook pro keys. It is very much solved in that. Just I wanted to convey what the meaning of this example is. See, this is the frequency response of the channel, C of f. Okay. So C of f, that is from minus W to W. That is 0 to W pulse having a magnitude of 1. And this is the shape of the signal which I am going to transmit to the channel. This is my GT of t. Okay. So how do we represent this mathematically? You just see it is given in the book. Okay. This is GT of t. When I pass this signal through a channel having this frequency response, at the output, means this is the in time domain, and its frequency domain will be like this. Okay. The spectrum of GT of t will look like this. So this has to be restricted to within this bandwidth. If not, then there will be intersymbol interference. So that is what I wanted to convey. Okay. So with mathematical equation, just have a look about that. And as I was telling about this intersymbol interference, so as I said, this is the input signal, right? A pulse. If I transmit this through a filter, if I consider that filter is a low pass filter, then output of the filter will be like this. Means there will be some change in the shape of that signal output of the filter, right? So this is the input data what I'm showing here, right? So as it travels through the channel, so there will be overlap of the adjacent symbols duration. So this is one pulse, right? So I get one signal like this. So the subsequent pulses. So these are the points where I say there will be an interference with the adjacent symbols. Okay. So the filtering effect of the band limited channel causes a spreading of the individual data symbols passing through it, right? So for consecutive symbols, this spreading causes part of the symbol energy to overlap with the neighboring symbols. So that leads to intersymbol interference, I'm saying. So is it clear about this ISI, intersymbol interference?
Yes, sir.
Okay, let me throw some light or Again, repetition about the master filter, because I'm not sure how many of you have remembered. So these are all very simple equations if you understand those things clearly. Let me take up that about the master filter. Just I wanted to throw some light on that. Let me stop this recording.